Okay, so classic problem-solving strategy. We've all been told that when we're confronted with a particularly difficult or complex task, we should break it down and take things step by step. Well, apply that sort of mentality to the study of materials and you get the finite element method. So, what is the finite element method? Is it A, a numerical method that solves for the reaction of a system given some force? B, a method to break the system into smaller parts that are called finite elements? C, an umbrella term for the array of mathematical techniques that fundamentally solve for the matrix equation Ku equals P, where K is the stiffness or system matrix, U is the displacement vector that we are solving or interpolating for, and P is the force vector. Or D, a sophisticated version of garbage in, garbage out. Well, the answer is all of the above, D included. Insert your favorite FEM or matrix solver like Abacus or MATLAB. You want to be able to see past that black box veil to be able to better understand the solution it spits out, and to potentially be able to troubleshoot your algorithm. While it's difficult to quote a date on the invention of FEM, we can say that its development can be traced back to the early 1940s to solve complex elasticity and structural analysis problems. To this day, FEM is a common tool in the use of solving engineering problems in other macro-sized systems. However, with the advancements of microscopy in smaller and smaller resolutions, such as with SEM or AFM, we've obtained a greater ability to investigate problems that are multi-scale in nature, which essentially looks at how phenomena like faults are a product of micro or atomic scale problems. With that goal in mind, many proposed FEM models came about to integrate these continuum to atomistic perspectives. With these different methods, there are three general aspects that differ from each other. Those are 1. How are the differences between continuum and atomistic scales mended? How are they integrated? 2. How is the energy in the system minimized and calculated? 3. The computation costs of the method. One of the most successful and popular models is the quasi-continuum model. The method chooses representative atoms along the system where the places where deformations or critical regions will have a higher density of those representative atoms. That leaves regions far out more coarse, and you can use continuum techniques over there. The second feature of QC models is its approximation of atomistic interactions. Like I said earlier, representative atoms are chosen in densities proportional to the region of interest. That leaves the energy too, approximated by those representative atoms. The last feature is automatic adaption with the method to minimize computation costs. When using FEM, typically you come in with a priori knowledge on what the problem is, and you set up a static situation with some forces and you preset your mesh accordingly. Automatic refinement allows us to have elements that vary in size with different regions of interest as the simulation goes on. An example of where the QC method can be applied is with Nano Indentation. Nano Indentation is a technique used for testing surface mechanical properties, such as stiffness. Current studies tend to focus on hard tissues and biomaterials, but soft tissues and viscoelastic biomaterials are also growing in interest. Elsewhere, we see that FE modeling can be used to calculate the dynamics of proteins. In particular, in a 2017 study by Yoon et al., the study took a critical lens towards the use of FE to 135 different representative protein structures. They found that it was more beneficial to use a contour surface of an electron densities as the mesh. In brief, another fascinating atomic level FEM method by Wang et al. 2019 was made to study the stiffness of cells, in particular cancer cells. Because stiffness is a key mechanical property that is closely associated with the biomechanical functions, such as mechanotransduction and the metastasis mechanisms, where mechanotransduction is the mechanism by which cells sense external stimuli, such as touch, and metastasis is the agent spread to different locations in the host body. They found evidence that the stiffness of cancer cells brings positional differences, inherent position. As we've seen, FEM, especially atomic level FEM, is a growing field and is powerful for its ability to model these biophysical systems as well as deepen our understanding of the kinematics and mechanisms of the underlying physics. So, thank you for watching.